hear me? Hello?
Yes, yes.
Yes, okay. So today, thanks for coaching kind introductions. Today I'm going to share with you this Taiwan quantum computing, its overview, progress, and challenge. Okay. Um, so here is today's outline. First, I will introduce what are the qubits and the motional levels, and I will go to these laser ion interactions. And using these interactions, we could do all sorts of operations, like the step preparation, the single qubit gates, the state detections, and two qubit gates. And at the end, I will share with you this, what are the progress and challenge in our field. Okay. So first of all, to track ions, let me show you how exactly do we track an ions. So as we know from these Laplace equations in 3 dimensions, it actually forming the solution of the saddle point, like the saddle surface, which means the ion will tend to go to the minimum as indicated as the blue region in this graph. So in order to track an ion, we need to oscillate these electric potentials in order to keep the ion in the middles. And this would actually correspond to the transverse confinement using the radio frequency field. And in order to confine the ion along the longitudinal directions, we actually apply an additional DC static field. Okay, so actually this idea lies the foundations for the modern ion traps, regardless of their geometries or their structures. Okay. Okay. Now let's talk about the qubits. So in ion system, each ion can represent a physical qubit. And the qubit levels actually corresponds to their internal electronics level. All right. And the Hamiltonians will look like this, and the sigma Gx represent the basis of the internal electronics levels. So there are many kinds of qubits in Taiwan system. So one way we're calling it is like the optical qubits and Raman qubits. The optical qubits means that this qubit will actually driving the direct coupling between the excited and the ground state. For the Raman qubits, we're driving this Raman transitions that couples the ground state and excited state through the intermediate state. Okay. Okay. So what are the choice of these internal electronics levels? So actually there are plenty of choice we can choose from, such as the hyperfine, Zeeman, and optical and fine structures. So we also call the qubit by their type of electronics levels, like the hyperfine qubits or the Zeeman qubits. And the most common one, I think, would be the hyperfine qubits and the optical qubits. Right? And here's what it looks like in the energy level diagram. And here, this diagram is showing the energy levels of the 40 calcium ions. And as you can see, that we have the Zeeman splitting, the hyperfine splitting, and the optical transition. So each of these transitions can effectively be used as our qubit levels. Okay. And there are plenty of iron we can choose from. So there are beryllium, magnesium, calcium, strontium, the cadmium, beryllium, or the ytterbium. And for our ion laboratories, we are actually trying to acquire this ytterbium and beryllium as our ions for the quantum computers. Okay. Now let's talk about the motional state. We know that the ions are the charged particles. So basically they're interacting with these Coulomb interactions. But in the same time, they're confined by these electric potentials. So as the result, they will form a collective motions. And this collective motion it has a classical analogs to like what we learned in classical mechanics, which is the normal modes. And in quantum mechanics, we will quantize this collective motion further into what we so-called orthogonals. Okay. And in a linear ion chain with n number of ions, it has 3 n modes, where the 3 corresponds to 2 transverse directions and 1 longitudinal directions. Okay. So here's what the Hamiltonians look like. If you could recall from your quantum mechanics courses, this is actually the quantized harmonic oscillators. Okay, and here we got the longitude. If we have 2 ions, there are 2 possible modes, like the central mass mode and stretch mode. And for the transverse, it follows the same way, but the only different thing is that it moves in the transverse direction. So now for linear chain of ions, normally we will have a stronger confinement along the radial directions, say the x and y directions, and we have the weaker confinement on the longitudinal directions, say the z directions. So here are the spectrum of the modes that we can have in a linear ion chain that is plotted with the number of ions against the mode frequencies. So as you can see, the left-hand part, the kind of have a larger frequency gap, and this corresponds to the longitudinal modes. And the right-hand side is the transverse mode. So you can see that the transverse mode has the higher mode frequencies because we are actually providing them a stronger confinement. Okay. And for the longitudinal modes, the center of mass mode has the lowest frequencies, followed by the stretch mode. And for the transverse mode, the center of mass mode has the highest frequencies, and the zigzag mode has the lowest frequencies.
So what's the vertical table n? Is the different table?
Sorry, what?
The vertical n.
The vertical, oh, it corresponds like, this is the center of mass mode. And then wait, let me show my pointer. Oh, so the vertical one, all of this corresponds to the center of mass mode, but they correspond to different number of linear ion chain. So, okay.
You mean higher number of linear chains?
Yeah, like you could read it like horizontally. This is like if we have 10 iron in the system. Here is the mode spectrum we will have for the longitudinal modes, which distributed at these frequencies along here. And here's the distribution of the transverse mode frequencies for 10 ions. Now, if you have 9 ions in the system, here's the what the mode frequencies will look like. Okay, and it will go down like until you have 1 ion. Okay.
Why there's a space?
Sorry?
Where is the space identity? Where there is a space, there's no.
Why there is the space?
The triangle shape.
Yeah, because here, like I said, when you look at it horizontally, this line represents the system with only 1 ion. So in 1 ion system, the possible mode you can have is only 1, right? For a single direction. So for the 2 ions, you have 2 modes for a single direction. So there's 2 modes correspond to the different frequencies. Yeah, and then it goes on straight forward to the 10 ions. Okay.
So the number of modes grows linearly with respect to the number of qubit in the chain?
It's not linearly, yeah.
But your class somehow shows.
Yeah, because it's 10 ions, but when you expand to the 100 ions, the pattern one looks like this. It will like curvy, like the quadratic, yeah.
How come number of ions didn't change the number of waves so much. I mean, they look like roughly oscillating in the frequency.
Number one didn't change.
I mean, for two ions and 10 ions, it looks the energy spacing does not look like very much different for the low energy levels. And it's periodic to the evening. If you correspond to a periodic system, but for finite system, your energy level difference looks like not change so much, or it's just because of the scale.
Yeah, it's because of the scale, but if you do it numerically, you will see actually there are slight difference on this both frequencies, but it's not quite visible on this scale like 10 ions. Okay. All right. Okay.
Change was more change.
Change what?
I mean, the change was more for more much difference than the usually change was more.
Yep. In fact, we did use. We are kind of in favor more or towards the transverse mode because you see we have a stronger confinement to this mode and it is actually insensitive to heating. So any force we throw at them, they will, because of the strong confinements, it will like insensitive to the heating. Yeah. Okay. All right. Okay. Yeah. So you know that we have the 2 degrees of freedom. The first one is the qubit levels, and the other one is the motional levels. So the complete basis of interest in ions actually is the tensor products of these spaces. Okay. There are 2 ways of looking at this, and the tensor products of the states, the E and G, and the motional levels, the N, is what we so-called the sideband. So the transition between this state is what we call as sideband transitions. So as you can see, the qubit levels actually have a larger energy splitting than these motional levels. Okay. Here's the sideband transitions. And okay, so there are 3 types of transitions. We have the carrier transitions, which does not depend on the motional levels. As you can see, you can drive the spin up to spin down or vice versa without affecting the phonon numbers. Okay. And there is the red sideband transitions and blue sideband transitions. In these 2 transitions, we are actually like modifying both the spin and the phonon number. Okay, so how exactly do we choose to excite which transitions? The answer lies in the laser frequencies that we chose. It is indicated by this red line and the blue arrows. Okay. All right, so these sideband transitions are actually lies the foundations for the operation that I will discuss in the following slides. Now let's take a closer look to the spectrum in the first sideband. So like I said, the frequency splitting between the qubit levels are actually very large. But when you focus on a single qubit levels and you magnify it to the greater resolutions around megahertz, this is what you will see. And the center one is the carrier transitions, which drive from spin up, between spin up and spin down. And when your detuning is tuned away from carrier transitions, and it is in the megahertz regime, that's when you are starting to see the motional sideband. Like I said before, when you have 3 ions, you have 3 excited modes, and followed by 3 radial modes. Okay, and this is what experimentals done with the frequency sweeping. They sweep across the megahertz regime, and that's what they found, that actually the sideband exists like in this 3-ion system. Okay. Okay. Then, so you know that in order to couple the qubits and motional levels, we need the interaction with lasers or microwave. And the complete Hamiltonians will include this electronics level, interaction Hamiltonians, and the motional levels. Okay, and now we ask the question, what could this laser coupling do? So we could do all sorts of things like the step preparation, single qubit gates, 2 qubit gates, and state detections. And I will explain each of these in detail in the following slides. Okay. Okay, so the laser cooling, the aim is to get to prepare a ground state and have a relatively low phonon numbers. Okay. So that the motional heating is suppressed. Here I will introduce 2 kinds of cooling. The first is the Doppler cooling. So basically we are using light to decelerate the atoms or ions. But the tricky thing is that the light has to be in resonance with the atom only. Then the atom can absorb the photon and absorb the momentum, which in turn give the decelerations. But you know that the hot ion or atom are actually moving constantly. So it's quite tricky to do this cooling. So what Doppler cooling does is that you can refer to the diagram at below. We are applying a pair of laser beam, which is red detuned, and this ion is moving to the right-hand side. So when it moves to the right-hand side, you see the blue shift, which compensate with the red detuned lasers. And this will give the resonance, make the ion resonance with the red detuned lasers in this direction. So it will kind of absorb the momentum and decelerate the ion. And as for the light from the other side, it won't have this effect because the laser is originally red detuned, plus it sees the red shift, so it cannot have the resonance with the ions. Okay.
So like the motion of here is from.
It's from the phonon, right?
I mean, so like previously, the atoms were like this, I don't know how to describe, right? There was, so like this motion is it also like generating some heat.
Yep, so that's correct. So
here to cooling, you don't even want like those modes to exist.
Yeah, like I say, yes, we don't. For the step preparation, we want the ion to be cool initially. Yeah. Okay. So after we do all sort of operation on it, it will start to get heat out. But later I will explain this operation. We are doing some sort of modulation in hope of like returning the ion back to its cooling state, its cool state.
So could you go back to a few slides? Another one, like energy shift. Yeah, this one.
This one.
Then next. Oh, previous. Yeah, this one. So like this one is like the energy level here is each energy level means different number of n is a number of ion.
No.
This
like I say, you will have the tensor product between the qubit levels and the motional levels. So the first line you can think of it like the up state cross the n. The n is the phonon numbers.
This is like the energy shift is like one motional mode to another one.
No, this actually like refers to here. For simplicity, here refers to only a mode. So what it does here is that when I drive the transition from down state to up state, it will gain me one phonon to a certain specific mode.
But it's still on the same motion.
That's depend on your frequencies, because let's say this is the center of mass mode. The N refer to the phonon of center of mass mode, but there are maybe like right above it, they are the N for the stretch mode, for example. So yeah, so there are many kind of this level. You can imagine. Yeah, okay.
So there are three kind of energy level. The N refer to the motional, and 1, 2, 3 refer to the channel.
Yeah, yeah.
And up, down refer to the qubit.
Yeah. Okay.
And you use the same thing for different group.
Why?
They all still belong to the same thing. Oh yeah.
Okay. Okay. Okay, that's how we basically do a Doppler cooling on the ions. Now, the example I show is for a single direction. So for a three direction, actually, you just need to apply the three pair of beams in X and Y and Z directions in order to cool the ions in the three direction. Yeah. And then the other type of cooling technique I would like to show you is the sideband cooling. So this actually have used the sideband transitions I have explained to you. First, we apply the red sideband transitions. So this will like make you lose a phonons to here. And then we wait for the spontaneous emissions for the E state to drop to the ground state. And we repeat the process. You will like from the G1 drop to the E0 and then wait for spontaneous emission and then drop to the G and 0 state. And this is how we do the sideband cooling. And actually, there are many kinds of cooling, but today I will just focus on two. Okay, yeah. Now let's talk about the single qubit gate. So here we are actually using the lasers to drive the carrier resonance, which means we don't have the coupling with the motions. And this is what the rotation operators looks like. And the theta corresponds to the drive strength and time, and the phi is the drive phase. So as you can see, at different time, it actually corresponds to different theta given by this. And this graph can, at different point, can drive different transitions. Like here, you can actually get the superposition state. Okay. All right. So I think this is clear. Now let's look at the real. So we are actually using the spin-dependent fluorescence. By fluorescence, it means the glowing of the atoms in the dark. So why is it glowing? It's because of the spontaneous emission. And by spin-dependent, it means like only like we choose a specific state, it will glow, and then for the other state, it won't glow. So for example, let's look at these energy levels, and we are choosing S and V as our qubit levels because D has a longer lifetime. And we use SP transition as the fluorescence detections, which means we actually have applied the lasers on resonance to S and P, and then if there is the population at S state, it will be driven to P state, and then the spontaneous emission will give out photons, and we will detect the light. But if there's a case where the population is in D state, then we won't get fluorescence. And this is how we tell whether the qubit is in the ground state or excited state. Right? And you might wonder that how about hyperfine qubit and Zeeman qubits? How do we do the real? So I won't go into detail, but the basic idea is that we can map the state in this Zeeman or hyperfine splitting to the D state and follow the same manners like in the previous slide. We can do the real. Okay. So now let's talk about two qubit gates. So before I get into, in these sections, I will like introduce first what are the simulated Raman transitions, which is lays the foundations for the continuous wave scheme, and then I will briefly introduce about the discrete pulse scheme. So here is the figure for simulated Raman transitions. It may look intimidating at first, but Actually, let me like decompose this. So C is the intermediate state, B is the excited state, A is the ground state. So A and B is our qubit levels. And the frequency splitting are given by omega node. Now we are applying a pair of lasers on both of the qubit levels. And the laser have the frequencies of omega 1 and omega 2. And the difference between omega 1 and omega 2 give a detuning given by the delta node. Okay, so by tuning the delta node equals 0, we can actually drive the Fourier transitions from between B and A. And in order to couple the motion and with the spin, we need to drive the transitions of the detuning close to the motional frequencies. So here we are slightly detuned from the motional frequencies, and we are not really actually on resonance with the motional frequencies, because we don't really want to excite the phonons, but we want to let it have the Rabi oscillations, which never really reach the n+1 state. And then using these cycles, we can drive the force for the ions. So by choosing the laser polarizations, we can select different forces for different qubit levels. In most of the cases, we will select an opposite Rabi amplitudes for different qubit levels. And please note that here we are using Raman transitions, and C is the intermediate state, which means we don't want any population to be reside on C. So this laser has to be far detuned from the C. Okay. As you will see later, this actually will pose a limit to the current gate scheme. Now, I'm sure you all know the qubit gates. So for tri-ion, it is more convenient for us to realize a control phase gate. Okay. Okay. So first, I would like to talk about the continuous wave scale. So the idea actually centered around the forced harmonic oscillators. You see now you have two ions, each has two qubit levels. And the interaction Hamiltonians, when you write it down, it looks like this. And from quantum mechanics, you can quickly notice that this is actually resemble the form of forced harmonic oscillators. And what are the term in front, the F, S1 and S2? So this actually corresponds to the superposition of the force between ion 1 and ion 2. Okay, so what we did, and the next step is to find the evolutions of these Hamiltonians. In the leading order, we will have the displacement term, which corresponds to the driving the ions in the phase space. Okay, and the next order will give us the logical phase term. And this term exists because the Hamiltonian does not commute at different time. Okay. So S1, S2. Oh, it's from the laser ion interactions. I didn't really show the Hamiltonians, but it's from there. Yeah. Okay. Yeah. So let's look at the most simplest simple models which will excite the Brownian mode. So like I said before, we can apply different forces on the qubit levels. And you can see immediately, because Brownian mode moving like they move oppositely. So when the state is in 0, or ground state, they see the same forces, but this will turn out to be into the cancellations, and they won't see any forces in 0 state. But when they are in 0, 1 state, they actually see opposite forces. But because the breathing mode pushed them to be like moving oppositely, so the force superpose into like the negative 2F. The same goes for 1, 0 state and then the 1, 1 state. So you would imagine like for there is only the trajectory being driven in the odd parity state, but not the even parity state. And this is just for the simplest model, but there are cases where force has been exerted on the even parity state. So under these circumstances, we need to tune the ratio between the ratio of the force between the even parity and the odd parity, so that the odd parities can gain a relative phase.
It has like the force is 2F, then like there is still motion like it didn't break the breaking mode, so I mean still moving like this. I just wonder, like, so the force just contribute to the phase.
Yep, yeah. So the phase actually come from like there's the forces right here. When you're expanding to the second order, these forces does not commute because of the bosonic operators. They does not commute at different time. So this gives rise to the phase. But if your term, like your cancellation F is 0, which means we won't have any non-commuting term for that specific spin configurations. Right? And so, like I said before, this is the displacement term and the logical phase term. And here's what it looks like. Okay, and you can quickly see that actually this is a term we want. This resembles the Ising ZZ operators. And this term is the thing we don't want because it gives erroneous transitions and hitting like the A apply on the motional state, it will like give you more phonons. So for a high fidelity gauge, we would want these A functions to be turned on during the gate operations. And once it's finished, immediately at this get time, we want it to be 0. In the meantime, this phase can be accumulated to pi/4. Okay. And here's what our fidelities will look like. So we are finding the difference between the ideal state and the real state. By real condition, I mean we are considering the effect of the noise term and the phase term. And by ideal, I mean we only consider the phase term, which is the Ising ZZ models. Okay. All right. Now, okay, let's look closer to what the alpha functions looks like. So when you write it down, it actually resembles this form, and you could quickly see this is why it can revolve around the phase space trajectories. And by choosing the t to be equivalent to 2 pi over delta, you could actually like move the ion back to its original positions. And here is the phase conditions, which proportional to the square of f over delta. All right. And now we ask the questions, which is how do we make a fast gate? You could see immediately that we can increase the detuning, but this comes at the cost of this phase condition, which is we need to maintain this ratio to be pi/4, which means the force need to be also like increased to a certain amount to maintain the pi/4 ratios. And by increase the force, I mean we need a higher laser powers. So, but this is not possible for our current scheme because, like I say, we have the Raman transitions, and this laser amplitudes cannot be like, must be much smaller than the capital detuning, like the off resonance detuning that I showed you before. So this actually poses limitations to the current gate scheme. But there are some solutions come out of it. So now let me explain more about it. So like I said before, for a diabatic gate, we want the detuning to be tuned close to the motional frequencies. So this will determine your gate speed. For a fast gate, and if we're using continuous wave, we can increase this detuning, but this fast gate based on the same idea as the adiabatic gate, but only we need to do a little modification to our theory. But essentially, they are based on the same theory. Okay, but now what I want to introduce next is the fast gate they are using ultra-fast discrete poles. So here, actually, we are not depending on the sideband resolving mechanism. And here we are driving the lasers on resonance to the intermediate states. Here you could see that the force only impart on the ground state, but not the excited state. And let's look into more details of how do we actually accomplish the fast gate. So here we have the ultra-fast lasers coming from two directions. And each lasers have each poles have the width of tau, and there will be delay between these two pulses that coming from two directions. And the repetition period is given by 1/Fr. So, and this is our qubit levels. And this is what we need to drive, like we need to apply the resonant transitions between here. So the ground state will feel the force, but not the excited state. And this is what Hamiltonians look like. And note that here, each pulses are actually the pi pulse. So a single pulse will drive, if the ion is initially at the ground state, it will be drive to the excited state. When it meets another pulses, it will drive to the ground state again. Okay. And there are timescales that we need to consider in this theory. So we need the laser repetition rate to be larger than the track frequencies, so that you could think of if the ion is in the oscillations, but this oscillation is slow enough for the laser repetition rate. So essentially, it will see the laser repetition rate as if it is stationary. And the second thing is that we want this laser pulse durations to be much smaller than the lifetime of P. This allows us to neglect the effect of the spontaneous emission from the P tree-half. Okay, now let's take a closer look of how exactly do we accumulate force from these kind of mechanisms. So you see that we have the force coming from the left-hand side first, and then the pulse from the right-hand side follows. So first, if the ion is in a ground state, it absorbs the pulse from the left-hand side and being pushed in the right directions. And then here, now it is in excited state, then it meets another pulse coming from the counter-propagating directions. Now, when it meets another pi pulse, it will go down to the ground state again. And this in turn will emit a photon. But due to the conservation of momentum, it actually pushed the ion another way and accumulated 2 h bar k of momentum. And you can imagine that we have a series of pi poles coming in from 2 directions. And this is how eventually we could accumulate a force for a single ion. Okay. So if you want to accumulate negative forces, the only thing we need to do is like arrange it in the opposite manners, like the negative K poles will hit the ion first, followed by the positive K poles.
How do you know the immediate photon will go in this?
Do you know the immediate photon? Oh, okay, because this is a simulated transition, not the spontaneous emissions. So actually, okay. Oh, okay. Why does the photon work this way? I think it's somewhere nice about around this conservation of momentum. That if we give a force in these directions, and yeah, it doesn't explain well. Okay, let me think about it. Okay, I think I don't have a clear answer right now, but I will answer to you after the session. Okay.
Sorry, I'm confused.
What?
The square, last pair are referring to the ion.
What? Can you say it again?
Last pair minus K refer to the ion.
K minus L.
Of the square, square. Are they keeping? Are they ion you are referring to?
Square. Sorry, I don't get your question.
Right. So your pulse is acting on the ion and making them to meet and absorb all photon.
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 Okay. All right. Now let's look at the progress and challenge of this field. First, I will show you the records of the single qubit gates and 2 qubit gates, and then what are the current feasibilities, and what are the challenge we have right now. What are intrinsic limit as we see from a theorist perspective, and yeah. And in order to solve this intrinsic limit, what are the solutions we come up with, like the scalable architectures and the parallel gate? Okay, so as you can see, there are many kinds of gate, and we call it mainly by its categories, like the physical implementations, we will call it, and then the spin bases, the gate time, and the laser control parameters. And now the fastest record that trap ion has is about 1.6 micrometers with the fidelities of 0.998. And it also can achieve like sub-microseconds around 500 nanoseconds, but the fidelity isn't really good. Okay, here they are using the continuous wave scheme and the sigma z gate, and this does not use the discrete pulse, and they are only using the amplitude modulation for this case. All right, and this is a summary of the gate's feasibilities, and the vertical axis is the power required for the gate operations, and the horizontal axis is the gate time. The left figure is for single qubit gate, and the right figure is for 2 qubit gates. In general, the laser power that's accessible by current laboratories will be around 1 milliwatt to like 100 milliwatt. Okay, so as you can see that in general, the gate time under current circumstances will go around like 10 to the power of -7 for single qubit gate. and it's around microseconds for the 2-qubit gate. Okay, and then of course, from the perspective of theorists, we always assume the experimental conditions are ideal. But in the real case, there are actually many problems happens to the lasers and the trap. Like they will have the field inhomogeneities, like post-timing errors, polarization errors, like and then detuning errors, intensity fluctuations, and optical phase drift. Besides, when you are using the Raman transitions, they will have this of resonance scatterings and this of resonance Fourier coupling. And for the trap, when your electron hits out, it will like give a fluctuations to the circular mode frequencies, and this will in turn give the heating, the micromotions, and the motional dephasing. So as a theorist, we can't really tune the limit of the instruments, but what they are currently doing right now is propose a robust scheme against these sensitivities. So like I said, we can do the amplitude modulation, phase modulations, and frequency modulations. We can even do it simultaneously to like make the error insensitive. So here are the plot of like what I have organized from the recent papers, and this is the error that they claim to be, they have made it to be insensitive. Okay. So besides the experimental problems, we would also have investigate the intrinsic limits of the tri-ion systems. Like the Lambda approximations will tend to break down when we are doing a fast gate. This is because the fast gate requires higher amount of laser powers. So Lambda approximation, you could think of it like the ion is oscillating. So when it's oscillating, you can think of this like wave packets, and the wave packets will be like applied by your lasers. So so if this wave packet is narrow enough, when the laser hits it, the ion will see the laser as if it is stationary, so it won't have any drifting or shift in the laser frequencies. But this changes when you hit the ion hard and it oscillates violently. So this will like give the the breakdown of Lambda approximations. Then in the same way, it will also lead to the breakdowns of harmonic expansions. Like the reason we can form quantized harmonic oscillators is because we assume this trap are given to the ion the harmonic motions. But when this breakdowns, you will actually see the coupling between the modes in the same direction or different directions. Different direction, this is what we call a pure coupling, which means the modes from the radial direction can actually couple with the axial direction at the higher orders of the harmonic expansion. And the other problem is the mode crowding. This is a scalability issue. When you put on more ion in the system, you will see the spectrum will get narrower and narrower. The gap between two modes will become close to each other. So, like I said before, if you want to like excite certain mode, it won't be possible because the neighboring modes are also in near resonance with the frequencies. So this is a problem with the mode crowdings. And the other one is that the crosstalk, meaning that it is hard to do two qubit operations or two CNOT gate on a single quantum bus. And this cannot be done unless there are certain modulations. Okay. So let me introduce briefly what are the scalable architectures. So there are 2D and 3D lattice where it can be trapped with the micro trap or the surface trap. And there are also method that we use to modularize the ion into different segments. And this is Qccd and photonic interconnect. So these are basically based on the same idea, which modularize the ion into different segments. So in Qccd, we will move the ion to the interaction region only when we need it. So this could effectively reduce the crosstalk effect, but it comes at a cost of connectivities between the ions. And for photonic interconnect, it follows the same idea, but this each linear ion chain is being confined in the ELU modules, and these modules is being coupled to the optical fibers. And these optical fibers will carry whatsoever informations in ELU to the central unit for computations. Okay, next, I want to show you about the recent progress in the parallel gate. So in this paper, like commonly we think that ions has the all-to-all connectivities, but this is not true until we can actually realize a parallel entangling gates on the near, like two parallel gates on the near regions. And it could really like provide the flexibility when you want to design quantum circuits. And this is what connectivity becomes meaningful. But before that, what we have been shown is that we didn't really show the parallel gates before until 2019. They started to look at this problem, and in this paper they find the limits of how long these two ions should be separated in order to like have a negligible crosstalk effect. And there is another research on a closed parallel entangling gates. As you can see, this is a pair, and the lighter colors one and the stronger colors one. So this could be done with a few modulation on amplitudes and frequencies, I think. Okay. And yep, by doing this modulation, they could effectively get rid of the crosstalk, say this between the lasers, this one and this one, but not from the local CNOT gate or the local 2-qubit gates. As for this, the other one is quite impressive. They take, it is from, I think from Tsinghua, and they take this crosstalk effect in considerations in order to make a 4-qubit GHZ state in a single run. So this actually saves a lot of time for when you want to design efficient quantum circuits. All right.
So they can reduce the gate used on the left-hand side.
Yeah, that is
one operation.
Yep.
Okay.
Yeah. So yeah, that would be all for me.
Okay. So hopefully you can get a nature as well.
Okay, is there any questions? No? Okay.
So I have a question either. So is it possible to extend this 4-qubit to like 8-qubit or anything follow the same principle?
Because in their paper, what they propose is arbitrary number of GHZ states.
Oh, okay.
Yeah.
That's very interesting.
I guess most errors can be like detuned away. Like if you can tune very well the laser, you can get rid of most errors. Or am I?
Get rid of the most error by.
For example, taper variation or like even crosstalk, right? Because I imagine crosstalk is like some residue of the laser going to or something like that. So I imagine you can reduce the amount of error very well if you can tune the lasers very well or something like that. Or how hard is it to get rid of errors?
How hard is it to get rid of errors? From a perspective of theories, we can easily like optimize a model to get a infidelity like 10 to the power -4 and -7. But yeah, but that's the ideal conditions. But like I say, in experimental conditions, things aren't always be perfect. There are this kind of errors. So yeah, there's a slight deviation from the real conditions and the optimization result we got.
And do you know roughly how it compares like ion traps with other architectures?
I think that I'm not sure about that, but I know one paper you can refer to.
Okay.
I will show to you later.
But suppose I'm thinking of spending money on ion traps instead of, I don't know, diamonds. Like, why do you know roughly or not? Like which one? Like, how is the game between like different architectures? Which one do you
Oh, okay. You're talking about what are the part of the ion trap that outperform the other architectures.
Yeah, or which one do you know roughly which one?
So the most, I think there are. You could think of this like the trade ion. They are actually like when you're using hyperfine splitting, they are actually very stable. Like compared to superconducting qubit, they like decay very fast.
Okay.
Then the other advantage is that, like I say, the all-to-all connectivities. This gives you flexibilities to like design a quantum circuit. But for superconducting qubits, they have like nearest neighbor interaction only, right?
Okay.
If I recall correctly, yeah.
And would there be many like good reasons why you want to do like other geometries like these ones that you showed in the last a string of ions, like having I don't know, like a grid of ions or something like that. Like, would there be any reason why that would be advantageous?
I think this should be look at this as in the direction of designing a quantum circuit, because what they are showing here is that we have these flexibilities of designing a circuit. So yeah. Okay.
So when you mentioned to our to the first top doing parallel effect, are you saying you have to control the amplitude laser of the
Yeah, we need to control control them in real time. And how to control it? Basically, we can start from a theory and then get the optimization parameters in the amplitude and the frequencies. And then we optimize and look for those parameters, optimize parameters.
Optimize frequency, or we have to make the shape, some kind of shape in
Yes, they did make the variations of the frequencies profiles for this paper. Yeah, they are actually using the yeah. Actually, this is the experimental realizations. Yeah, so it's already been done in 2019. Okay. So like maybe I will add on for this one, they actually use the amplitude modulations and the phase modulation all together. Okay. Robust gate scheme.
What kind of issue you concern for all these issues?
Oh, what's the issues we are concerned with the robust gate scheme? Like I said, because the experimental condition isn't always the ideal, so we were like assume the worst case, maybe not the worst, like and not ideal experimental conditions and start from there. We want to like design the gate scheme that is insensitive to these experimental errors. So yeah, so even if the experiment has this kind of errors, we could like design the gate scheme to like make it robust against these errors.
So, is there any question from the audience on the online? Okay, then thanks Wen Han for this talk.
Okay, thank you. So, is this it? Okay, goodbye. Goodbye.